Okay, so this is the R for the power and effect size week. So what we're going to do, we're going to have two halves to it. The first, we're just going to go through, do what we did in class and just go through all the previous tests we did in the 1 and 2 sample tests, but calculate the effect size. For that, some of these are in Excel spreadsheets, so we need to be able to load an Excel spreadsheet, XLSX. We're also going to use a library called Power. The first one we're going to do is length of stay. Remember, for single samples, the relationship between the T and the Z and the effect size D is they're basically D times root n. So to get the D, we divide by root n. So we're running the test using the standard t-test. We can get the t-value using the test or statistic, and then we divide by square root of n, which is just the length of the data vector. So we just load in the data. This is our data. We're just passing it as a list vector of numbers. We do the t-test. We get the t-statistic. And then we just divide. We're gonna do the mu0 first. We were skipping a step. So we get the results, and then we have the t-statistic, and then basically we divide by square root of n. And then we output it using the sprintf function, and there we have the effect size is minus 0.1278, the same as we get in the slides. Corporate sustainability, remember this had a large z-score, but also a large magnitude of z-score, but also a kind of a large sample size of 992. So we got, we think it's incredibly significant, but our effect size is actually not that big. It's minus, it's a smallish effect size. So let's just do this, and we do exactly the same. I won't go through it in detail, but again, we take the statistic and divide by square root of n, and we get the effect size of minus 0.27. And then for the single samples, we're going to kind of finally, the third one, this is the T example. This was the emissions test. So we have this very small sample size of size 10. And testing at alpha equals 0.01, we just about failed to reject. But because the sample size is so, is so small, this was actually on a pretty large effect size. Remember that the Cohen's effect sizes are 0.2, 0.5, and 0.8 is large. This is a large effect size. So do the emissions, exactly the same. I don't need to go through that in detail. And the emissions D, effect size of minus 0.8. Okay, next for the two samples. And what we do here is, because it's not as directly related to the t-test, if we use the Cohen rather than the hedges, the Cohen's D rather than the hedges G, I basically define a pooled standard deviation. So we can have the standard pool standard deviation, which is the one used by the hedges G and the one used by the student's t-test, which for the sample, we're just correcting by subtracting by 1 for the first standard deviation and 1 for the second standard deviation, and for 2 for the combined standard deviation. And for the Cohen's D, we're just not doing on the bottom. We're getting the maximum likelihood estimator there. So we just have these two different estimates which you can get from this function. You see the only difference here is for the standard one, we have minus 2. Basically, if you type in Cohen, you get the top one. And if you type in anything else, you get the bottom one, you get the standard one. So just a little function there. And to just have the function in memory, we've just got to run it. And it doesn't do anything, it just stores the function in memory so we can utilize it. So here's the auto example. So if you recall, this was our Japanese cars in the US and Japanese cars in Japan, and we wanted to see whether Japanese cars were being sold cheaper in the US than in Japan. And we failed to reject. And we had the effect size. The effect size was kind of smallish there. So we have minus we have basically have a small effect size of minus 0.3, a small negative effect size. And we actually calculated the hedges G. So let's just run it. So we get the data to calculate the D. We basically have the difference between the two groups, so x bar 1 minus x bar 2 divided by SD. But we've got the Cohens, and then we have the hedges. The hedges is minus, there's not a great deal of difference, so minus 0.3236. And it pretty much agrees with what we got in class. Okay, so this was the success. And again, we're going to do exactly the same. Remember, this was a pretty significant test. We had a low p-value. And to get such a significant test on what is a pretty small sample size of group 1 with 12 and group 2 with 15, we actually, we have a huge effect size. We have an effect size of nearly 2. And you can see that from the Excel data. You can see that, look, compared to the standard deviations, there's a huge, huge difference between the means. So let's do exactly the same thing. Here we're going to load in the Excel spreadsheet. Now, if we look at the success, all the values are kind of in one. We have like 2 different ways of doing it here. So I'm just basically saying, okay, when for group 1, when column 2 is 1, return the success, and when column 2 is 2, return the success. So this is basically the rows. This is true whenever it's a 1, true for group manager group 2, and this is just saying we're taking the values in the first column, which is the success. And again, the D is the difference between the 2 groups, and then the divided by the pooled standard deviation. And again, for hedges G, we get 1.9239. So we get this kind of whopping large effect size there. Okay, so remember, this is where we went to the book. Now, this is when, I emailed the author of the textbook to say, hey, your values are different from G power. I triangulated with R. R has a function called power.ttest, and we can just look at it here by doing a question mark. Okay, so basically with the power.ttest, we pass the number of observations, the effect size, and power. You pass 2 out of 3 of those. So if we want the power, we'll pass the effect size and the N. If we want the N, we pass the power and the effect size, etc., etc. Also pass the significance level, the type of the test. Power.ttest, this is for t-test. So do we have a 1 sample, a 2 sample, or a paired sample, which we're covering next week? And then the alternative hypothesis, are we doing a one-tailed greater than, one-tailed less than, or are we doing a 2-sided? So that kind of specifies. So just go through the first example. So here we go. Okay, so we have this big effect size at N1 equals N2 equals 10. And it gives us a power of 0.875, the same as G power, a little bit less than the book. The second example, this is the Martian example, where we have M1 equals N2 equals 8. And again, we have a big effect size because it's the height between males and females. We know this is different. So we shouldn't need a big sample to find this. And this, even with a small sample, should have reasonable power. And the power is a little bit less than, it's the same as G power, a little bit less than the book. And as I said, after speaking with Barry Cohen, that's because he used the normal distribution. And the T distribution is a little bit wider, so it's a little bit harder to reject. So this is the kind of the example that we did in class. But we're going to do it for the T test. But the T and the Z here are relatively similar because it's a large sample size of 100. So again, we're going to get exactly the same that we get from G power. We get a power of 0.98, which is the same as the table. because again, the table uses normal, and this at a sample size of 100, the t distribution is almost converged to a normal. Okay, so estimate d from power and n. We have a power of 0.6, and n1 equals n2 equals 10. And we get a d of 1.05. Again, because we're using the t distribution, the d's are a little bit higher, the powers are a little bit lower. And next one, we do it for kind of the single sample version of the test. Note here that we pass one sample rather than two samples. And we get a d of 0.784. So again, a little bit higher, though not as high as with the two sample test. So we need, for one sample, we need slightly less effect size to get the same level of power. Okay, so on the final stretch, so we're going to do, we did that one. Okay, so we're estimating n from power and d. So we've got the minimum acceptable power is 0.7, and we have a small effect size of, to find a small effect size of 0.2, because we have to find, we want a high power for a very small effect size. We can imagine we've got quite a large n. And we're going to do two samples and one samples. Oh, sorry, so next slot down. And here we go. We get n as 310 and n of 156. And again, very, very similar. And this is because for the large sample sizes, the t and the z have almost converged. But if we want differing, this passes like, we're passing when we're doing these. So say, for example, the last one, we want to find the power and we have n and d with differing n's. So we can actually calculate the harmonic mean for the n and plug that in. But funnily enough, R has one where as a power.t2n.test, where you can actually pass in the different n's. So you don't have to calculate the harmonic mean, which makes it easier. And there we go. We get a power of around 0.4, which again is kind of consistent with our, powers being a little bit lower and the equivalent effect and the effect size needed for a certain power being a little bit higher. I.e. with a wider t distribution, it's a little harder to reject. Okay, that's it.